Hello everyone and welcome back to another episode on complete reference to CUDA programming. In previous episode we have seen the performance limiting factor was a single thread block, and because of which there was a poor resource utilization on the GPU side. Now to overcome that problem, we said that there is a solution that we can launch multiple thread blocks. So in this episode we'll try to explore the possibilities of launching multiple thread blocks and what are the limitation factors for that also. So to understand the same problem with multiple thread blocks, I'm going to consider the input size, which is going to be sufficiently small here for the understanding purpose. So let's say input size equal to 8, that is n equal to 8 here, and I'll consider number of threads per block equal to 4 here. Now I want to launch total number of threads equal to input size, so I'll consider here number of blocks equal to 2, and which in turn gives me total number of threads equal to 4 into 2, that is 8. So 4 is nothing but number of threads per block and number of blocks are nothing but 2 here, and hence I'm getting total number of threads equal to 8, which is exactly matching with the input size, that is 8. Now we have two thread blocks to perform that same task of vector addition. Now again, if I use the same logic that we used in the previous version of the vector addition, let's see what happens. So I'm having two blocks, so I will have the index that is starting with 0 for these blocks. So I'll be having block 0 and next I'll be having block 1. So let's focus on first what is with the block 0. So if I use the same variable thread idx.x, then block 0 threads are responsible to perform addition on first 4 elements indexed from 0 to 3. Now if I'm having block 1 now, but problem is that here again I'm using the thread idx.x variable. Again I'm having 4 threads, but the variable that is, or we can say the index variable that I'm using to perform the addition, which is based on thread idx.x, and that is again giving me local thread IDs within the block. For block 1 also the thread idx was ranging from 0 to 3, and for block 1 also it is ranging from 0 to 3, and because of which the block 1 is also getting assigned to perform addition on first 4 elements of these arrays. And obviously this is going to be wrong result, because we were expecting these 4 threads to work on the next 4 elements, but unfortunately because of our the way we have written the code, the first 4 threads are getting allocated to first 4 elements of block 0 from the block 0, and again the next 4 threads from block 1 are still getting allocated to first 4 elements of this array addition, and that's why we are getting these wrong results. And the culprit here is thread idx.x, that is local to the thread block. Now question is how to resolve this problem. We want to ensure that block 1 to perform addition on next 4 elements indexed from 4 to 7 here. To do that, we have to come up with a global ID, right? So what do you mean by global ID? So this thread idx.x is giving me ID which is local to the thread block. I want to come up with a way so that the ID of this thread is going to be 4, ID of this thread is going to be 5, this thread will be 6, and this thread will be 7. So that once I get those IDs, block 1 will be responsible to perform these 4 elements, right? So that is our ultimately aim in this particular exercise. Now question is how to compute these global thread IDs. To understand it better, let's consider a couple of scenarios. So in this case I have considered vector addition kernel, and I'm launching one block with 8 threads. So in this case this variable is going to give me number of threads per block equal to 8, that is block dim.x. So these are the variables which are very important in order to understand how to calculate this global thread ID. Now the grid dim.x, which is going to give me total number of blocks that I'm going to launch in this particular kernel right? And that is here 1, because I have launched only one block. Now if I change this configuration little bit and I say I'm going to launch 2 blocks with 4 threads in each block. Now in this case, what happens? The block dim.x becomes 4 because we are considering 4 threads per block. And at the same time, grid dim.x is going to become 2 because we are launching 2 blocks in this particular kernel. Now if I twist again this configuration and if I say I'm going to launch 4 blocks and 2 threads per block. So in this case, what happens? Block dim.x becomes 2 because we are having 2 threads per block, and grid dim.x becomes 4. These two variables are going to be very important in order to calculate the global thread ID. Fine. So I hope you got to know about this block dim.x and grid dim.x variables, how those values changes inside the kernel. Now coming to the point, how to calculate this global thread ID. So you can see here I'm using a variable int gid. You can name anything you want, but rather than only rely on thread idx.x, I have added few more computations here using block idx.x and block dim.x. So this entire formula is going to give me global ID. Now, so let's try to investigate for each and every thread from these blocks how this gid variable is going to change. So let's take first thread 0 from block 0, and for this particular thread what is the value of gid. So for this particular thread, gid equal to thread idx.x, that is value 0, block idx.x, so it belongs to block 0, so that id becomes 0, and block dim.x, that is nothing but total number of threads per block, and that value is 4 here. So for thread 0, gid is going to be 0. Now for next thread from the same blocks number 0, thread idx.x becomes 1 because that is a local thread id, and block id is still 0, and multiply by block dim.x, that is going to be 4 always. So for this thread 1 from the block 0, gid becomes 1. And for thread 2 and for thread 3, it becomes 2 and 3 respectively. Now this is for block 0, and you can see in block 0, thread 0 was responsible to perform addition on 0th elements of A and B. Thread 1 was responsible to perform addition on first element of A and B, and so on. Now let's try to understand what is happening in case of block 1. So this is block 1. Now inside block 1 again I'm having 4 threads, and let's focus on the first thread here. So its thread id is going to be 0 because the thread idx.x gives me local thread id. So this becomes 0, but block idx.x is 1 now because I'm referring to block 1 now, and multiply by 4, which gives me total number of threads per block, that is block dim.x. And if I do this addition and multiplication, so I'll get gid equal to 4. Now for this thread 0 from block 1, gid is holding value 4. Now next thread, I'm having thread 1 from the block 1, and for that thread if I put the values in the same formula, so it becomes 1 plus 1 into 4, that is 5. Now gid variable for this particular thread is going to be 5. Now same for thread number 2, it is going to be 6, and for thread number 3, let's see the final one. The local thread id is 3 here, plus block id is 1, and multiplied by block dim.x, that is 4, so it will give me 7. And now you can see this thread is working on 7th element of the array, right? So this is how we can solve the problem of mapping multiple blocks to same array elements by calculating the global id. So let's try to understand using code how we can modify this particular kernel now, right? So in next episode I'll elaborate the coding part. Thank you.